below the Earth's crust holds its history. While most of the Earth is covered in its oceans, its biggest secrets remain hidden. A group of international scientists aim to uncover the mysteries of Zealandia, Earth's sunken continent. In order to complete this mission, the scientists will set sail on a 2-month expedition on board the Joydes Resolution. The Joydes Resolution, or JR, is 143 metres long, and its derrick stands 62 metres above the waterline. It can drill in water over 8 kilometres deep, and then drill down into the sediment over 1,600 metres. By recovering sediment and rocks at the bottom of the sea, it provides scientists a glimpse into Earth's past. The scientists look to understand how the Pacific Ring of Fire formed in the Zealandia region, as well as Earth's climate at the time.
So we're not doing anything tricky. Essentially, we're going and doing routine stuff in a new area rather than fancy stuff in an old area. And so oftentimes the real problems come if you're trying something, like technologically different, and then it doesn't work. But we don't have that issue. So we're using effectively old technology, but in a totally new area.
And wrapped up in all of this is the element of exploration, because so little is known about this region. So we have a more fundamental goal of just exploring this continent.
1.5 to 2.5 years before an expedition takes place, one of us staff scientists and project managers are assigned to an expedition, and that's when we start preparing for operations and also to get the science staff recruited who's gonna join this expedition and carry out all the shipboard work.
So we've got 126 people, I think, sailing on the ship right now. The science team is only 30, but we have a bunch of technicians, and we need everyone from, the cook and the cleaning all the way to the captain to make this adventure work.
With all the pieces in place, the scientists spend their last days on land getting used to their new home and taking part in meetings as they prepare for the 2-month expedition. They need to be up to speed and ready to work as soon as they reach the first drill site.
On the expedition, our role is mostly to get all the scientists trained, coached into a very intensive workflow. So we work 24 hours around the clock. We work in 2 shifts. These 2 shifts have to receive course, describe them, and do analysis in a coordinated fashion so that everything's done in a consistent manner and everything's being written up in time. Everything's is done for one site when we move to the next site, and just to make sure that within 2 months we do all the work and we conclude all the work and we have everything written up takes some level of coordination.
The ship will not dock again after leaving port. Scientists, technicians and drill crew will work around the clock 7 days a week to ensure no time is wasted. Excitement mounts as they leave the shore for the adventure ahead.
We're getting ready to depart here from Townsville on our journey into the Tasman Sea to sample the Tasman frontier. There's a sense of excitement and a sense of adventure for the things that we're going to find when we drill into the Lord Howe Rise and to the rest of Zealandia. So everyone's really excited.
I am sailing for the first time, so I'm pretty excited, as well as a little nervous too. And I'm Joyita Bhattacharya. I'm sailing as a shipboard sedimentologist. This is my first time doing a science expedition.
This is my first time sailing as well. I'm sailing as a shipboard paleontologist. So I'll be looking at the tiny fossils that we bring up from the seafloor and helping everyone else kind of interpret what age that sediment is. So we're going to be working as a big team. This is the first time that I'll be working with a team this large with scientists from all over the world.
My name is Margot. I'm the palynologist on this expedition, and I'm also going to be doing a bit of organic chemistry. So that basically consists of checking the gases, seeing if everything is safe. And palynology is me looking at these really tiny fossils called dinocysts, and they can determine the age of the sediments, but also what the sea level was. So they're pretty useful bugs, really.
This expedition is so amazing because we're going to be looking at a new continent and basically going where no drilling bit has gone before. So it really does feel like we're explorers in a real sense, where we don't know exactly what we're going to find.
As the science party take their last look at land for the next 2 months, the Geordies Resolution sets sail for the Tasman Sea, targeting 6 drilling locations.
So we left Townsville. Just to get to the first site is 4 days. And so if you think on a modest-sized research vessel, it usually goes out for 3 weeks or so. But if it takes you a week just to get there and a week to go back, there's not much time to do stuff. And so these drilling expeditions, on average are about 2 months long. So ours is, just about 2 months. That's sort of what the time you need just to put in 6 holes, and so it's just a major operation.
Co-chief scientists Rupert Sutherland and Jerry Dickens, along with some of the science party, have spent years determining which drilling locations would give them the best results in order to study the sunken continent. None of the 6 drilling locations have been drilled into before.
4 of them aren't. The nearest drill site previously is on the order of 250 to 300 kilometers away or more. To give you one of the fascinating things about Zealandia is how few holes have been drilled in this part of the world. So yeah, sure, lots of geology has been done on New Zealand, and to a fair amount on New Caledonia also. But the areas in between, the vast majority, let's say 95% of Zealandia or so, which is underwater, other than petroleum wells right along the coast in New Zealand, just the number of holes that have been sunk to understand these tape recorders of time and to reconstruct the tectonics are just remarkably few.
It's a very remote region, Zealandia, and it's under deep water. Most of it's more than 1,000 meters water depth. And so to collect a sample is very difficult. And it's made even more difficult by the fact that it's covered in a fine pelagic mud that just rains out of the ocean. And so to actually get down and see through that requires that you drill beneath the seabed. And so it doesn't happen very often.
After 4 days of transit and hours of preparation, the Geordies Resolution has reached the first drilling site. In order to begin the coring process and start recovering core samples, the drilling crew goes hard to work and assembles the drill string.
We have 12 thrusters. They're roughly 750 horsepower each, and 2 main props, which I think we have over 2,000 horsepower on each prop when we're in DP mode. And the DP system uses a combination of GPS signals and a combination of acoustic signals, because we put a beacon on the seafloor. And between those two GPS units and a single acoustic unit, we have 3 separate signals going into the DP system to tell us where we are at any one point. And the DP system will give the thrusters and the propulsion units a command telling us where to go. We're measuring where we want to be, where we are, and how to get back to where we should be.
We have to make up the bit and the bottom hole assembly, or BHA. That's the very bottom of your pipe. And the purpose of your BHA is for weight. When you start drilling, your bit's on the very bottom. You do not push down on the bit with your pipe. The connections on it are made that they always have to be in tension. You can't put them in compression, they'll fail. You don't ever want to push down on your pipe. So what you do, you put these larger pieces of pipe called drill collars at the bottom, and those are used for weight. And depending on how many you have determines how much weight you can push down on your bit. And that's the first thing we do, we put that all together. The pipe is made up in stands. A stand of pipe is 3 singles of pipe screwed together. We can on average run about 25 stands an hour. Each stand is about 29 meters in length. So depending on the depth, you can calculate pretty easily at 25 stands an hour how long it's going to take you to get to the seafloor.
The drilling crew work through the night in order to have the first core on deck by shift change the following day. In order to recover sediment from deep below the seafloor, the Geordies Resolution has developed a deep sea drilling system that has resulted in many significant and exciting discoveries over 4 decades of expeditions.
The ship never stays still, the ship moves constantly, and we use a dynamic positioning system to keep the ship within a certain percentage of the water depth. The drill string is extraordinarily flexible, and our critical limits are 5 degrees and 8 degrees of water depth. So you've got a 50-meter circle that you can make in 1,000 meters of water. In 2,000 it's bigger. And it doesn't act like you think in terms of going off at an angle, because we have a pendulum, if you will, on the bottom of the drill string. We have a bottom hole assembly, which typically always hangs straight down, even when it's in the ground.
We have a drill bit on the end of a very long pipe, and that has a physical weight. And we use some of that weight to actually push onto the bit and drill the hole. Even though the string is steel, and you think of it as we think of steel as being nice and strong, when you've got a 5,000 metre long piece of it, it's literally like spaghetti in the water. So it twists and turns and bows and buckles if you're a bit rough with it. So, and the result of that can be something as simple as you don't drill a straight hole, or you end up breaking equipment.
It's hard to really tell how much is moving from up here. You know, it could be bowed considerably, but we really don't know. We assume that's another purpose of your BHA, is to keep the pipe straight. You know, you've got all this weight at the bottom, pulls it down, it keeps it straight.
It looks like the pipe's moving up and down, but in actual fact the pipe is stationary and the ship's moving around it. It takes a while to get your head around that, especially when you see it at first. But yeah, basically it's just a giant air cushion that operates above us as part of the equipment in the derrick, and it just ensures that the bit stays on the bottom no matter what we do.
Additionally, we have a heave compensation system, which acts much like the shock absorbers on a car. When you see it working, you'll see the big pistons going in and out. We actually support the entire weight of the drill string with air.
The drill string itself is hollow. We pump fluid down it, and that fluid on this rig is just seawater, but it cools the drill bit and it lubricates the hole. But more importantly, it flushes out the drilled material. Yeah, so it's like if you drill a hole in a piece of wood, you get sawdust out. Well, we call the rock that we get out cuttings, so it flushes the cuttings out. So we've got a nice clean hole.
You know, we've got 3 basic core systems, the APC, XCB, and the RCB.
There's something called APC coring, which is essentially taking a straw and like poking it into jello. So you build up pressure and just poke into the hole. And that gives you beautiful cores, but you can't do it as soon as the sediment starts getting hard. Then you can switch over to something called XCB, which you start turning and drilling, and if things are good, then you get a really nice core. But sometimes it does what's called biscuiting and breaks the whole core up, and it looks terrible. And then there's the old-fashioned way called rotary coring, which most people try to avoid, which takes the big bit and just sort of drills right into the material and goes down.
With the drill string assembled, the coring process has begun. It is now time for the scientists to put their years of research to work.
The first drill site, of course, is a big adventure for everyone. Most scientists have never worked in a big group like that. And being faced with the challenge of working collaboratively in a large group is new for most people. We rely on some senior scientists or some people who have sailed before to help coordinate this and make sure that people figure out how to work together in an effective manner.
It's a long time ago that we work on this project, but not me, Julian and Rupert work a lot of time and spend 5 years of their life to understand and to prepare this kind of mission. And we are lucky that the boat is coming in this part of the world.
You know, I've been working in this area for about 10 years now. I did my PhD 10 years ago. But since the Zealandia continent is underwater, we only work with data that is indirect, so only images of what's beneath the seafloor without any touching really the true geology. It really is a discovery. Lots of drillings, they happen in places where we more or less know what we're going to get. Here we have hypotheses, but I really think the discovery part is going to be very big. We might find things that are totally different from what we were expecting, and I think that's really, really exciting.
Rotary coring was selected for the first drill site, as a strong seismic reflector indicated a transition from soft sediment to hard rock.
In the initial expeditions that were done to explore Zealandia, there was very little in the way of seismic reflection imaging which allows us to see beneath the seabed. So what we're looking for when we look at a seismic profile is we're looking for the stacking patterns of sedimentary layers. By looking at those stratigraphic relationships to features that we can see, like volcanic centres and ridges and basins, we can date when they formed.
While the science party is expecting to hit hard rock, they are unsure what they will recover.
So now the continent of Zealandia is mostly submerged at the exception of New Caledonia and New Zealand. And so we are recovering cores from under the sea to look at the sediment and go into the past. And by trying to give an age and give the type of sediment that we recover, we can reconstruct the history of Zealandia. For example, as further we go down into the cores, we can encounter sediment that were deposited at very shallow water depth. And if we are able to date these sediments that were deposited at shallow water depth, then we can reconstruct the different phase where Zealandia was not submerged but potentially exposed over the water.
After recovering over 20 cores consisting of nanofossil ooze and chalk, the science party hit hard rock and unearthed the first pieces of the Zealandia continent.
We actually reached our target this morning. We penetrated from the nanofossil ooze that's in Eugene age. I think we went down from the Pleistocene back into the late to middle Miocene, and then at a very sharp boundary we penetrated these volcanic rocks, and we knew that they were there from the seismic profiles. We didn't know what they were, and so the two, I think, competing speculations were that they were either a carbonate reef or they were volcanic rocks. So it's not necessarily very unusual to find these, but we just didn't know, and so it will be important now to date these rocks.
So this is core 29R, and this is the very famous, like very much wanted boundary, which is like Eocene Oligocene boundary, and this is the very first specimens we recovered from Zealandia, the 8th continent.
Exactly.
Yeah.
And so we have enormous breaks in time, or as the geologists would put it, loss of the geologic record. And so here we go from 23 million years ago, which is a third of the way back from dinosaurs, all the way back to a time about 46 million years ago, which is about 2/3 of the way back to the time of the dinosaurs. And then this little boundary here, this is the contact between the ocean and a volcanic edifice that we think is part of Zealandia.
It's several million year hiatus or a break in record.
This mineral is one of my favorite minerals. It's called glauconite, and it's spelled this way. And this glauconite is indicative of where there's very low sedimentation rates, basically a condensed section where sediments are just not being deposited. And so this whole section here is basically where the sediments are just barely being deposited. So we may have actually a long amount of time span for just this very short interval here.
And all we can say right now is that this is strongly altered, and you can kind of see how we have some lower parts. This is a flow boundary here. You see the upper part being altered and the lower part being much fresher. And so you go up again here, you see again from fresher to more and more altered, and as you get to the top of it, it's strongly altered. And my guess is, I'm not an expert on this, but my guess is this is definitely subaerial. So that they were exposed to weathering for a substantial amount of time before the next lava flow was deposited on it.
This was a one-shot deal, and so we feel fortunate that we were able to recover such an amazing, exceptional sedimentary and igneous rocks succession here.
A lot of research will go into this part, I'm sure.
Yes.
While the discovery of the volcanic rock has the science party buzzing, it has come at a cost. The time it takes to drill through volcanic rock increases recovery time immensely. They must now decide whether to continue to drill at a slowed pace or move on to the next drill site to keep on schedule.
We have drilled into volcanic rock, and
It was sandy at the top.
Maybe there's a little bit of sand at top.
There's a little bit of sand on the top.
It is volcanic rock. So we are in a bit of a situation. We forgot to staff some meteorologists to help us. But I'm sure everybody went through Geology 101, in undergrad, and we'll do our best. Just a bit of a warning. So I think we can very safely say it's an eruptive, it's a volcanic and extrusive rock, okay? But what it is, it can become very tricky.
The plan is to, once it's cut in half, we're not going to touch anything out here. So we're not going to, we don't want any high resolution sample because we really want to understand it first. But it's imperative that we take, let's say, 2 samples right above to look for the micropaleontology and ideally the XRD. And so it looks like it's glauconite in there. And so one idea is that there's this funny interval in the middle that's about 40 centimeters long. And if that's got a bunch of shallow water microfossils and glauconite, we've solved half the tectonic problem here, and it's just fantastic.
The reason why it's interesting is because on the seismic sections, there's a layer, not just a single reflector, but 2 reflectors really close together, which is probably something about 30 meters thick maybe, and then there's another reflector that comes in with the reverse polarity, which is indicating something soft underneath, that comes in just underneath that. So around about where we are, and we just had a drilling break in the last one, it got a bit softer, and so I'm intrigued as to whether we're just going to go through and go back into some sediment underneath, because we don't really know what age these volcanics are.
So these sediments here were 45 million years or so, 46. The sediments below this volcanic interval may have been as old as 55, 56 million years ago, which is during the time of the Paleocene. And that's the time interval just after the dinosaurs became extinct. Yep. So it's getting cooler and cooler, but we had to weigh the options and we decided to move on.
Co-chiefs Rupert Sutherland and Jerry Dickens have decided to pull up the drill string and head to the second site. The volcanic rock will be carefully labelled and stored to be further studied back on land.
So the volcanism that we found about, we don't know the age exactly yet, but we'll figure it out, probably between about 45 and 50 million years ago, was part of the formation of the Pacific Ring of Fire. There's been very large changes in the geography of Zealandia through time, and in particular, that event caused very large changes in the geography.
So there's one main hypothesis for the inception of Zealandia, and this hypothesis says that Zealandia detached from the supercontinent Gondwana around 100 million years ago. This led to the drifting of Zealandia towards the east, and which was also simultaneous with the opening of the Tasman Sea. So the opening of the Tasman Sea has made a part of the supercontinent Gondwana detached, so this is Zealandia, drifting away from Gondwana between 100 and 50 million years ago.
There's a shallow seafloor in this part of the world. We've known that for quite some time. But it wasn't really until about 20 years ago where people first started putting it together, and especially around New Zealand area, and suggesting that, all these, instead of little bits and pieces, this is all sort of part of one continent that's just happens to be submerged in one area, but it's all linked together. So all the way from New Caledonia to New Zealand out to the Chatham Islands, this is all part of one block of continental crust that's connected.
Zealandia was discovered in the 1970s, really, when people had just invented the theory of plate tectonics, and they went out and they mapped the world's oceans and discovered that there was a large submerged continental mass off in the vicinity of New Zealand. But very little was really known about it, so it wasn't really clear that it was a continent in its own right.
Starting in the late 90s, there were issues with law of the sea and trying to define international boundaries and who has rights to certain parts. And this part of the world gets sort of interesting because you have New Caledonia, which belongs to France, so they have an international boundary. You have New Zealand, which has quite a long coastline. Then you have Australia with these little islands like Norfolk Island and Lord Howe Island. And so each one of those gets to put their boundary around it. And so when you add them up, they all sort of connect into each other. And so there's parts that you have to decide. You have to say, well, who does this belong to, this part of the seafloor?
We know it's a big mass. It's very big, it's huge, but we don't know much because we don't have much direct geological evidences. We have ideas of, for example, the thickness of the crust it has, but what is its really composition, we don't really know. We know it was attached to Gondwana a long time ago and that it separated. We know roughly when did that happen, but what was its history after that, we don't really know. And that's why we're here, to discover all that.
There's been 2 previous expeditions that have been quite focused on looking at the sediment that's accumulated, and ours is looking a little bit deeper and with a little bit more background knowledge of several decades of surveying to really focus our studies. So it's actually only the 3rd expedition to go and sample these deeper rocks.
What's very particular with this continent is that it's totally submerged underwater. It was very stretched, and by stretching, it sank under the water, and it's today lying between 1,000 meters and 3,000 meters of water, which is quite original for a continent.
Now that it's underwater, it's collecting all this material over a huge latitudinal range. So in theory, we could collect all this sediment and think about it as tape recorders. So when a continent block is above land, it's being eroded. On the other hand, when a continental block is underwater, it's collecting sediment. And so it's almost unique in the sense it's a continental block that's, for 90% of it or so, we're collecting information about climate over the last 50 or so million years, which has changed dramatically.
The site in relation to DSTP 208 and 588, and in relation to our site we're at now, 1507. And it shows the black lines, which are the seismic lines. And then I've got a couple of figures. So just the next figure is just here. Yep, this one here, which just illustrates the fact that we have an upper seismic unit, which is very easily mappable around the region.
After a day of core recovery at the second drill site, the science party has continuously pulled up biogenic ooze, ash and chalk, interbedded with turbidites. A turbidite is a type of sedimentary rock composed of layered particles and mixed sediment.
You have a first greenish layer which look like turbiditic or gravity with some flame structure at the base. And you have the second event with more foraminiferous and finish here. After we have all the mud and the nanofossil ooze and another layer, greenish layer, look like volcanic ash, and we have a lot of biotumulation inside.
So is that biscuiting there, or is it almost
it's like fake biscuiting? It's like the same sort of thing that happens during.
Well, there's shear from the liner, and the rocks get
fracturing, twisting.
Oh yeah, I see what you're saying. It's twirling, and here look.
I was starting to fracture. The brakes. So what's happening? I think it's trying to turn inside the liner, and it's differentially turning.
So what we've seen so far is, as far as I understand, what I've seen, a Cenozoic hodgepodge of all the surrounding highs, expressed as turbidites and slumps.
So that brings up a thing, and so fortunately, when Rupert put this in, this was not the main. This is sort of, if we get some Pliocene material for people, great, but this was never one of the high priority sites for anyone working on the Neogene, and it wasn't the high priority for anything to do with the tectonics or the Paleogene.
Well, we've got more of this type of stuff till somewhere between, I can't remember the exact number, but more than 300 meters of it. And then we've got a zone of more reflective material, which I suspect a lot of people will be interested in. We have yet to sample it, but it's much more consistent in thickness across the region and more likely to be representative and more stable oceanographic conditions, producing more continuous record. And we don't know how old it is, but it may well be Paleogene.
But I don't think anyone on this cruise is particularly interested in a giant turbidite mess, for hundreds of meters.
700 metres below the seafloor is the target depth for this site. Currently the drill is at 400 metres depth and has hit a hard layer of sediment, which is producing poor core recovery.
We're now at 28 meters below the rig, so it's coming up, and as soon as it hits zero, that means the core is back up. The core barrel's back up, but we don't know what's inside of it. And it'll be about 10 minutes after. Yeah, my guess is we're going to have to do rotary coring eventually on this hole. Problem with XCB, it works really good in some lithologies, rock types, and not so good in others.
In order to save time and continue using the current drilling system, the drill crew is using a new technique.
Yeah, this last core, they switched it out, the method, so the water flows up into the pipe and through the pipe rather than blowing out the side.
I had a group discussion, and if it keeps on going bad, then we've got plan C.
Sorry, you've had a group discussion?
Yeah, well, I've talked to all the people on the ship about possibilities if this keeps on, if we have problems for it. You didn't exactly tell the truth on the last one. A hell of a lot of water that came on the deck. How much core? Water on deck. Some.
Got one section of similar materials, so
the question is, what do we do? Do we just keep on going like this? Because it's it's hard for us to work on this stuff. Pull pipe and go to rotary, and that would probably improve things a lot. But
it's doable.
Yeah, it's about 80 centimeters.
What do? You wash down to here?
Yeah, exactly. Yeah. If the next one comes like this, then I think what we do is pull up, move over, get the upper two cores by APC, then pull the pipe, and then come back and wash all the way down to the interval. Well, wherever the stuff starts getting interesting when they tell us, but they haven't opened them up yet. So
right. Okay.
That would be I think my preference if this next one doesn't work.
You got plenty of time to open them up while we're doing that.
Exactly.
The round trip will take 16 hours.
While the scientists wait for the next core on deck, they take a closer look at the cores filled with turbidites.
But what's weird is that they seem like well-defined classes already,
Yeah, that's what you think. This is amazing.
That's really good.
Yeah.
There's pieces that are really good, and then there's other pieces, that are just terrible.
These have occurred so regularly now, and they always look exactly the same. I tell you, it's always that much each time. That's why it's hard to think that these are
not circular cycles.
Seriously. Each time I look at the core, we have about 2 or 3 of these.
But you can see it's been totally biscuited.
And in each of these intervals between these green ones, we have sort of 1, 2, or 3 of these turbidites with the black forearm.
Oh, so you think these are completely unrelated to the turbidites?
That's what I think. Yes, I think that's 2 totally different stories.
And as Peter's saying, this goes all the way to the top.
You've taken a record of each of the green layers. Yeah.
Can you go find out? Just for fun? Because we're gonna have to, if we do.
This is the first one I've seen one.
If we do pull pipe and come back with rotary, you need to know where to start.
Exactly, it's the same thing.
Yeah. Oh yeah, you're right. Yeah, we name it this every time. We name it with nanofossil clays, with ash or with glass.
Yeah. No, my gut feeling is that these are important. These are the oceanographic cyclic type of situations or rare situations.
Yeah.
And then the foreign turbidites just come in. Randomly. Sometimes we have 2 or 3 between 2 green layers, sometimes 1.
As the scientists continue their discussion, the next core is brought to the surface.
I can't say you're going to do better than that with the rotary system, but if you keep doing that, I don't know how long it's going to keep doing it. It's getting pretty hard on the end.
Yeah. So.
Yes.
At this rate, we'd be another 5 days or something.
Well, maybe they just want the one hole in it. Maybe.
Although this one went the full, right? So 10.
Yeah, this is full.
So there's a problem. It's taking a long time, and the cores are not full, and they're coming up like in blocks. If the sediment changes, and we're starting to get long records without all the biscuiting, then the strategy works. Although it's still going pretty slow. It's just we're in this limbo land. We don't know what method. So I'm still heading towards, like, soon we switch over to rotary. But the problem is we have to pull the pipe and then put it down, so that kills a lot of time. So, but on the other hand, the ultimate goal is to get good records. And so yeah, we're still stuck. But this way, the advantage of just waiting one more core is that my colleague gets up and he can make the decision, so I'm off the hook.
In order to produce the best recovery from this site, the decision has been made to switch drilling systems. The drill string is currently in 3,500 metres of water and another 400 metres below the sea floor. Switching system and returning to their current depth will cost the science party an entire day.
In our original plan, we had we were going to double core APC XCB down to 700 metres to plug 700 metres at this site, right? So we had a big amount of time allocated and 3 logging runs, and we're essentially drilling the section once now, the top half with APC XCB and then the bottom half with RCB. So we're basically only really drilling one hole. There's a bit of extra time in the trip, but so we've cut that drilling time down by a lot, and we're only going to do 2 logging runs where we've trimmed that a little bit. So if all goes smoothly, we should go away from here several days actually ahead of which we can use later on.
We came to the decision because we wanted to go down to about 800 meters below the seafloor, which is quite far. And at around 350, suddenly, well, about 200 meters, the APC cut out on us, so we couldn't push ahead anymore. And then we went into the XCB mode, and that just started cracking all the sediment. So now we're stuck. And so we sat here for, quite some time thinking back and forth. This is a major gamble. Because once we pulled the pipe and went back down with rotary, if the rotary was worse than the other stuff, then we're in big problems. So we took the gamble, and for whatever reason, in that particular sediment sequence, the rotary coring just worked beautifully, and we just suddenly got these absolutely, just truly gorgeous cores coming up. It's looking good, Steve.
This is easy money. It's core after core, they're all good.
It's looking pretty good. Yeah, we have a lot of sediment in this core, so that's great. Always good.
Another good core.
Should probably just take a quick glance here, just to. This is what we're coring right now. It's this beautiful limestone that's got all sorts of banding in it, but it's mostly calcareous limestone. Absolutely great cores, as you can see, just the detail. We have to go where the wonderful people that study little creatures live, and they are down at something NP17, NP18. So we're in the late Eocene, nominally somewhere around about 38 million years. We have this funny thing called the MECO, which sits a little older than 40 million years, and at the current rates, we should be able to just capture MECO tonight.
MECO means the Middle Eocene Climatic Optimum, and it occurred around 40 million years ago. It was a warming event in the middle of a long-term cooling period.
When we go back in time, we see that carbon dioxide, which is a greenhouse gas, was much higher than it is today. And as we know, climate is changing, and it's warming up because humanity is putting greenhouse gases into the atmosphere. One of them, the most important one, is carbon dioxide. And so going back in time is kind of like basically kind of looking to our future. And what's important about Zealandia in this area in the Southwest Pacific, few climate records we have, they show that it's unusually warm, warmer than what the climate models predict. And so one of the key objectives here is to construct some long-term records going back in time, back to time intervals when CO2 was higher.
As they continued to drill through harder sediment, drilling slowed. The scientists had hopes of recovering MECO. However, most of the MECO was washed away or lost during drilling.
It's a little bit frustrating for some people because, we have some people that have come to sail for like their primary interest might be, a certain time interval, and then we go drill and that time interval is missing.
Yeah, so we're pulling up pipe here. The pipe's still about 3.5 kilometres long down to the seabed. We were intending to do some more logging, some recording of information down the hole. But after the first run, where we looked at the shape of the hole, we could see that the upper part of the hole was starting to get very narrow, and the hole was trying to collapse, basically. So we didn't want to risk putting our tool down there. Another few hours and they should have all of this pipe neatly stored away on the back of the ship, and we'll be ready to go. Drill site number 3, which is about 2.5 days steaming to the south, and so we'll be heading straight past Norfolk Island down to northern New Zealand. We've drilled 2 sites, and we've managed to get to or exceed our target depths of drilling, and we've discovered really interesting new observations that a lot of people would have difficulty predicting given the existing knowledge of the region.
What's been fascinating so far is when we drill these holes, so far we've drilled 2 of them, and neither one's quite what we expected.
I'm very satisfied that we've got a very unique record from this last site that has totally changed our view of how a sedimentary basin that is about 1/3 the size of India formed about 50 million years ago.
During transit, the scientists work hard to get all the information recorded from the previous site. A large part of the information they need comes from fossils found within the sediment. But how are the scientists able to give an age based on these little creatures?
One of the things that we're looking for is to develop climate records from millions to tens of millions of years ago. And the best way to do that is to get undisturbed sediments where there's no volcanics, no earthquakes, no underwater avalanches. We call those turbidites or turbidity currents. And the best type of sediment is where we have microfossils, basically, who live in the upper part of the ocean, living, dying, and then floating down to the sea bottom. These are called nanofossils, and the larger ones are called foraminiferous. Nanofossils, which are the really tiny fossils, there are about 100, you need about 100 of them to cover 1 millimeter. And the other one is foraminiferous that can get up to maybe 0.5 millimeter in diameter. And so those sort of sediments are great for us, because what we can do is we can do the geochemistry of these fossils, and they can tell us a lot about the paleoclimate.
All right, so right now what they're doing is they're pulling the core catcher off, and then they're going to pull out the core liner from the core barrel. The core liner is that plastic tubing that fits inside the metal core barrel and holds the core. We replace those each time we take a new core. So here comes the core catcher. You can see that's the very bottommost portion of each core that's drilled.
Material in there is the oldest material from that core. There'll be a paleontologist at the ready to receive the very bottom section of that core, so they can try to determine the age, the maximum age of that core. And as we progress into the hole, they can keep us up to date on how old we're getting, which is very important to perhaps how deep we're going to go.
You know, dating a continent is a pretty complicated thing to do, because what do you date? You need to know what you're dating. So we could say it's very, very old as Gondwana, since it was a part of Gondwana. But then what happened? And I think that's the whole point of this voyage. What happened during the 60 million years, last 60 million years? And that we don't really know. It seems some things happened, and we're here to find out what.
Yeah, we need to find marker species, so we know the range they occur through time, and then we record the occurrence in the core catchers.
Change of certain species or genus or families of a fossil, like it might be a nanofossil like a coccolith, or might be a foraminifer. So the change from one species to another is, or maybe the range that talks about the change in time, how their evolution is occurring. So that is the scale we use, which is called biostratigraphy.
In order to determine the age of the sediment, the scientists search for 6 fossil groups. Foraminifera, calcareous nanofossils, radiolarians, organic walled dinoflagellite cysts, polynomorphs, ostracods.
So there's 6 fossil groups on the ship, and there is kind of a hierarchy of who gets the age first. Not all the fossil groups are used to tell age, only a few. Others are used to tell paleo depth, so how deep the water was at any point in time. But the first ones to get age are usually the calcareous nanofossils. These are super, super tiny little fossils. When the nanofossil workers get a piece of sediment, they just kind of smear it out on a glass slide, and there can be thousands to millions of fossils within any one slide. So they usually get age first from any core catcher.
So I'm interested in generating a long-term, low-resolution sea surface temperature record from the Miocene to the present. So I'm sort of sailing undercover because that's not quite the primary scientific objective of the cruise. Here's a picture of a foraminiferal ooze. These are single-celled calcareous microorganisms that live in the photic zone, and they die, rain down onto the seafloor, and generate the sediments that we look at. So we take a little smear of the material, put it under a glass slide, and look at it through this petrographic microscope to quantify the various components that is in the sediment.
In smear slide, we see that there's a lot of calcareous nanofossils, and so that's the dominant factor in all of the smear slides. But also within these smear slides, we find some forams, and they range anywhere between abundant to rare. And interestingly, in this slide, we found what we think is a pollen. So it's the only one we found so far, but...
The discovery of pollen from land plants revealed that the geography and climate of Zealandia were dramatically different in the past.
The planktic foraminifera worker, so like what I do, it takes us a bit longer to get age from any core catcher. So we have to go through a more complicated process. It takes a bit longer to process our samples. So we have to wash the sediment, we have to dry the sediment, and then we have to sieve it in a little sieve, and then we look at the entire assemblage that's there and pick out fossils. The nanofossil workers don't really have to pick out fossils, they're just noting what's there because they're too small, you can't do that.
The JR operates as a floating research vessel. It is equipped with a lab for the paleontologists and a fully functional chemistry lab. The geochemists study water extracted from the core, as well as search for another type of fossil.
I study organic walled dinoflagellate cysts, and that might not mean a lot to you, but they are these little plankton that live in the surface ocean. And I try to get them out of the sediment to be able to date the sediments. After I take my sample, the first thing I do is I use strong acids to dissolve all of the other fossils that are in there, to dissolve all of the other minerals, so that I'm just left with the organic material, since my fossils are made from organic material. I sift the sample so that I don't have the really tiny stuff in there and I don't have the really big stuff in there, but I'm just left with the fossils that I want to look at, basically. Then finally, when I'm left with just the fossils I want to look at, then I put them on this little glass microscope slide, and I study that under this light microscope. When I'm looking at the slide under the microscope, then I try to look for different species. So I try to find species that are specific for a certain age, but also I try to find species that are specific for certain habitats to reconstruct maybe how warm it was, how salty the water was, things like that.
All together, we work as a team, so it's really important that we're talking constantly in the lab when we're together. For example, if the nanofossil worker is getting an age and maybe I'm a sample or two behind, which is kind of normal when you have core coming up so fast, I'm still talking with her, him or her, but what I'm seeing and confirming the age, or maybe I'm seeing something weird, maybe they're seeing something weird, so we always have to be in communication.
Each group, let's say the people studying fossils, they have to be talking to the people that are studying the sediment. And so that each day we have to have a meeting so that everyone from the different groups connects with each other. And so the groups are connecting, and then within each group they're connecting between day and night. We have to work together as a team because of the complications of what we're getting, and no one person sees everything. And so each group's sort of blind a little bit, and so we have to have this constant communication between the groups. So because the operations are going 24 hours a day.
The paleontologists and geochemists get to work on the core catcher, which is at the bottom section of each core sample. Meanwhile, the remaining core is measured, cut, and placed on racks until they reach a determined temperature. The physical properties team determine how long each core must cool before being split. Each core must be at the same temperature to ensure all measurements between cores are equal.
Everyone has a very specific task on the ship. So I'm part of the team that looks at the physical properties of the cores we're going to bring back. I will be just sampling the cores and looking at a whole bunch of different physical properties, such as the density, the velocities of the waves through the cores, and a whole bunch of other physical properties to get as much info as we can.
Once the cores have equilibrated, whole round measurements are taken. The cores are run through thermal conductivity tests and radiation levels are measured. These tests give the scientists insight into the cores before they even see inside them. As a safety measure for the scientists and drillers, a headspace sample is taken. A headspace sample tests for gases present and is needed to help drillers determine if it is safe to drill deeper, preventing drilling into any high pressure or high gas environments.
Once all of the measurements are completed for the sections prior to B-splitting, so the whole round measurements, thermal conductivity, then the sections can be split. So this could be anywhere from 5, 6, 12 hours after we've received the core. So then we go ahead and split the sections into an archive half, working half, deliver them to the appropriate tables, and then the science parties in the description lab and the physical properties lab can get to sampling and describing, and off we go.
What's very interesting in geology is to look at the records of the Earth in the sediments. So the sediments are basically either living animals that die and fall on the seafloor, or they could come from a volcano, or they can come from land. They just end up going in places where it's deeper, and they fill in these gaps. They fill the gaps. And these actually tell us the history. So the whole aim of this voyage here is to get cores from these records, these sedimentary records, and try to understand what was Zealandia's evolution since it broke up from Gondwana.
When we are working on a course, in fact, we first act is to describe the core. We identify the color, we identify what minerals or elements what we have in a cores, and then we describe when we have to put this core in different scan. So scan that we have is on image, so we take a very high definition of each half cores, and after we make some analysis like magnetic susceptibility or reflectance color from cores.
So this is a good example of a core that we just described, and so we record the change in the sediment type. So for example, here you've got a white section that is more limestone deposit, and this limestone is sharply overlain by more clayey rock, and there's a very sharp contact here, and all of these rocks contain fossils that provide us with ages. And actually here, the fossils told us that there is a big time gap between these different rocks. So we know here, for example, that there are several million years that are lacking here, so there was erosion going on Zealandia, and that's the kind of information we are really looking for. So if there are widespread erosion, how is this local, or is this recovered in all the sites among Zealandia? So that's the kind of information we can retrieve from the sediment core.
As the drilling progressed at Site 3, a large amount of limestone was recovered.
This upper limestone, this sequence is incredibly recognisable in geophysics, and we can trace it for 1,500 kilometres and map it across this entire region. Really related, so that's really quite cool. So now that we understand what this unit is, we can look at the regional distribution of these facies over really an enormous region.
Along with the limestone, the scientists are recovering mixed sediment.
So these units are being eroded and put here.
You see there's a truncation here, which moved the stuff on the top originally. You see if it continue going here, there should be stuff over here, like you see the lines, but these layers on the top like chopped the top and then dumped the stuff to the left over here. So that's why we found older stuff in this area, which should be younger than that part, but we actually found stuff which with the same age as this stuff because they are dumped here.
So we're still in the late Eocene.
So we're in the late Eocene, even though the fossils are mostly early Eocene.
Interesting.
Because they're being eroded.
The scientists hope to log this hole. By dropping an instrument down the drill string, they can take physical measurements of the hole. Logging data can compensate for missing time intervals in the recovered cores. They decide to drill deeper. However, the core recovery has slowed from once every 30 minutes to once every 2 hours.
It was just going so slowly that Jerry and I decided that there was no point in staying here for several more days just to get through it, so we decided to call it.
Drilling in deep sea waters can be unpredictable. The scientists must be ready to adjust their game plan with every challenge the ocean throws their way. During the logging process, an unexpected problem slowed operations.
The logging tool became stuck, and it was down in the hole, and to get it out, we ran the pipe down over the tool, tried to get it back up in the pipe, and then freed it up.
Fortunately, it all worked out. We got over the tool with the drill pipe, freed the tool, pulled it up, and then we're also able to free the pipe, because that's then yet another risk that the pipe gets stuck. So you have to do. So everything's back up. Cost us a few hours, several hours. We left this morning, and we should be arriving at the new site tomorrow morning.
As the research vessel heads further south, another complication looks to send the expedition off course.
The target is somewhere between 600 and 650. That would take us into tomorrow. Now we have a little bit of an issue. Bad weather is expected.
With a storm on the forecast, the captain will keep a close eye on the radar. Strong winds and high waves can make drilling unsafe. The JR is equipped with a dynamic positioning system that allows the captain to monitor the heave of the ship. The heave is the up and down movement of the ship when the sea is in a swell.
The DP system has a feature what we call the MRUs. They actually measures the heave, the roll. All movement can also be seen on this system. With the actual one, we can have the basis of the scientifically proven pictures from which and the average heights for certain wind. As you can see, the low is just passing Wellington and we are around the edge of it. In the next few days, there will be another low pressure system coming to our location.
Drilling is going well at the fourth site. The cores being recovered are Eocene in age, about 50 million years old. This is an important interval for both the tectonic and climate change questions.
So in general, this is generally what we expect. We wanted to get into this interval. There's the view that maybe the sediments are a little bit older than we had originally expected. The issue is, should we switch the mode of drilling to try to enhance the recovery during this period of time? But that will come at the expense of getting to the bottom of the hole. The reason why this has become more important is because there's going to be a storm that's going to come over the ship in about 4 days, probably on Friday.
It can be a lot better with half core. In what you would get 3 meters in the 10-meter advance, you would still get 3 meters in the 5-meter advance. That would be far preferable.
It is uncertain how much time the scientists will have at this site, so every decision becomes more important. Switching drilling systems or slow recovery could cost the team hours they don't have to spare. Seismic images and geologic interpretations give the scientists an educated guess on what they will recover. However, there is a level of uncertainty.
All the time. That's why there's scientists on board. That's why they just don't come out here with a robot and just drill, and then 2 years later, scientists look at the cores. Many decisions need to be made in real time, and that's what's going on right now. In fact, that demonstrates the important power of having a fully integrated science team on the vessel, because we can make these very informed science decisions which very much affect the operations of the vessel.
As ship heave exceeded 3 meters, drilling operations stopped and logging was cancelled. The captain called for WOW, or waiting on weather.
WOW is waiting on weather. So waiting on WOW actually is being decided on a lot of factors. First is the safety of the vessel and the crew. With regards to weather condition, more than 40 knots wind, and dynamic positioning capacity, holding capacity, if the vessel can still hold its position, and with the drill floor. The forecasted swell or maximum wind wave is around 10 meters or more. So we have to leave the vessel around 200 nautical miles or more, depending on which area is more favorable to the vessel.
The research vessel must now sail north to avoid the severe weather forecast. After the storm breaks, they will turn around and head south to the 5th drilling site.
I mean, realistically, we'll lose 2 days out of the schedule once we start moving and have to move back and so forth. And 2 days, so we have still one day reserved in there. So effectively, it could be as little as half a day that we lose, and in the worst case, it could be more.
For where we're at, this is probably typical, the weather. And we haven't seen weather like this in quite some time.
Heavy winds and rain cause the ship to jump and bounce as it sails, making for a choppy transit north. The harsh conditions cause many sleepless nights, as the ship leaps with every wave that crashes against the bow. Bungee cables are handed out, and the scientists are told to secure their workstations, as the movement of the ship can cause items to fly off their tables.
the weather's starting to get a little bit rough, and so things are rolling around, and a little bit later I have to watch my coffee because it might go flying off the table or something.
With the winds picking up and big waves spraying onto the ship, areas of the vessel are shut down and the doors are isolated.
Well, usually we isolate all doors going outside the ship, especially when the waves are, coming on, spraying on, wind is too strong. Sometimes it's also the problem regarding opening of watertight doors. Some personnel actually get caught while opening or closing the doors.
The scientists must now spend time waiting on weather. While the brunt of the storm is miles away, rain and heavy winds can be felt.
Whenever you go to sea or anytime you go on an expedition, there are a lot of things you can't control. The weather, of course, can't control. I found that this science party is very good at responding to the situations that they've been handed.
After the storm passes, the JR makes a 380 nautical mile transit south and arrives at the 5th drilling site.
We're in week 7. We've arrived at the 5th site. We've just had about maybe 4 or 5 days waiting on weather.
The scientists must now refocus for the final stretch of the expedition.
Drilling is a very long process and the area is so huge. Going between several sites takes several days, and actually doing the drilling, just getting a core that's 400 meters long, takes a very long time. Drilling is a very slow process.
At the start it's a 2-month mission, so you're slightly nervous when you say, oh, it's a very long time on the ship, but actually there's so much work and so much excitement around all the new data coming, all the new cores and all the teams working together that we are actually really busy, and so it's time flies, to be honest.
The recent weather delay has got them out of their rhythm of constant workflow.
It's always nicer when cores are coming up. It's more fun, more interesting, curious to see what's beneath the seafloor, so much better when things are moving quickly.
In my opinion, like on the ship, where we have come to work on these rocks, on the cores, this is the main objective of our work. Yeah. So if they are coming, I am happy.
Sometimes we are in a rush, sometimes we are not in a rush. We have time to get some free time, like a ping pong match. But we work every time and with different flow, and this is cause of timing to core.
With the location of the final 2 sites in the South Pacific, the weather will continue to be an issue.
It's always a bit stressful because if you're not experienced at going out on these sorts of voyages, then you're not necessarily mentally prepared for the other things. You may be mentally prepared for working long hours, but you're not prepared for when suddenly a bad storm hits or when a piece of equipment breaks and you're not making it to the next site, or the drilling just doesn't work. You just cores coming up empty, for example. That sort of stuff happens, and so each one of those is quite a big disappointment for people. So when you take 7 weeks of that added together, then you have to sort of balance up. It's that excitement of what you discover balanced up with the realism that you don't always get what you want, and sometimes you don't get what you want at all. So some scientists will go away just having no material that they expected to get at the end of the voyage, but we will have recovered some very interesting stuff that nobody expected to get, and so there's opportunities there. But it's quite stressful and difficult to be able to spot those opportunities and turn a problem into an opportunity.
To be prepared for the possibilities of another weather delay, the science team approached this site with a new strategy.
Basically to drill the top 50 meters and then only core 50 meters, drill ahead for 150 meters. That saves us 1.5 hour wireline trips and a total of almost a day, or about a day, just by drilling 150 meters instead of coring it in the uppermost sequence. Then go back to coring and then core as far as we get in the available time. if we don't do the drill ahead and we caught the entire upper interval, we risk to just run out of time to drill the lowermost interval.
Not everything goes to plan. That means that you have to change your drilling strategy and your coring strategy. So in part that's operational decisions that you make from hour to hour and even from day to day. But then the last couple of sites here, we've even been communicating with shore to try, and particularly the last site, to try and come up with some options that are achievable in less time if we only have that. So we can still discover something really interesting, even if we had only 2 days instead of 8 days. You know, what could we do?
With a new plan of attack, drilling starts at Site 5. After only recovering 3 cores, the weather strikes again. The scientists are forced to pull out of the hole as the ship had difficulty maintaining position and work became dangerous on the rig floor.
We've just advanced 27 meters. Unfortunately, the second core was totally empty. Actually, 2 cores were basically empty. The second and the third. So we don't have great recovery yet. We then have basically Monday, Tuesday, Wednesday, Thursday to go.
The weather subsides and drilling continues. While the weather delay causes a pause in core recovery, it gives the scientists time to catch up writing their site reports.
As well as collecting the material and planning and working out what we're going to do next, we have to analyse all the material which is brought up, and we have to write it up. I mean, before when we get off this ship, we're going to have several hundred pages of documentation of what we've already found. And so that's quite hard to be doing all of that all in one go. So everyone is just working flat out.
Drilling concludes at Site 5, and the scientists make their way to the 6th and final site.
I think there's plenty here for everyone. We've discovered an amazing range of different things that no one really expected. Obviously it's hard to plan for that, but I think that overall it's been very successful so far, and I'm really excited by the last 2 sites because they're key pieces. Now that we're starting to really piece together what's been going on, it's really becoming clear what place these last 2 sites have and how they're special. So yeah, fingers crossed, eh? Fingers crossed.
Upon arrival at the final site, the scientists are able to take a moment to look back at what they have discovered.
Now, one of the highlights of this expedition was actually that we were able to drill into sediments and recover sediments that were deposited during the time of the dinosaurs. These sediments here were from ocean basin that was relatively deep, thousands of meters. In terms of feet, there would be 10,000 feet of water depth perhaps. And what we saw is that the sediments suggested to us that the waters were pretty stagnant, not moving much, and where basically oxygen levels were really low, and there was also dissolution of the calcium carbonate. And so based on the fossils, it suggested a very enclosed ocean basin.
In the first hole, the volcanic rocks we found was at below Middle Eocene. The change from sedimentary rocks to volcanic rocks was just at below Middle Eocene. We see these nanofossil oozes, carbonate-rich things slowly transform into a small layer which is rich in glauconite, which is a very different indicative mineral, clay mineral, and then it sharply grids into volcanic rocks, and actually those are the samples from the Zealandia continent.
Before drilling, you always have a lot of hypotheses on what you're going to recover on the cores, and yeah, we had some nice discovery. We found a lot of volcanic rocks that were not expected, and so we don't know yet what are the age of these volcanic rocks. It's a good discovery, and it will surely give us new information on the tectonic history of Zealandia, because volcanic events are intimately linked with tectonic events.
Drilling has started at the final site. As core recovery progresses deeper, the scientists believe they have recovered Miko, a time interval they have missed at previous sites. In order to determine if the cores recovered are of Middle Eocene age, the scientists must date the sediment.
So in core 16, in the core catcher, I found this specimen. It's called Arthrobotrys B. aurita. This one in the center. So in that core catcher is the last time I seen that species, and the next core catcher further up it disappears. So then you can roughly use. So we know the last occurrence was in that core, and we know the datum, the age it occurred the last time. So we know roughly the age of that interval. And all the other nanozoans, benthic, planktic, rats. So at this site we fortunately don't have any calcareous microfossils, so the radiolarians are the only fossils actually present in the sediment. It's pretty interesting.
Christina found some radiolarians that can give an age constraint. And then, we have to go with the parameters we have. Here, it's like brownish ochre, and then it turns more reddish here. Start turning reddish here. It goes reddish down to here, and then the color changes back again. So like this. So it's possible that this changing in color corresponds to the Miko event. Warming peak, you have also the peak in magnetic susceptibility and iron.
The radiolarian fossils recovered from the core catcher show Miko in age. In order to help prove this age, the magnetic stratigraphy of the cores must match.
What we do is looking for the magnetic polarity reversal through the sediments. The magnetostratigraphy measurement consists in two phases. So we measure both the archive valves, so this course that you can see here is actually moving right now. The measurement is finished. So this is the archive valve. That means this valve has been measured for magnetostratigraphy. After this, it got wrapped and it goes in the archive, and it's not going to be touched.
After further studies on the magnetic stratigraphy and similar age of the radiolarians, it is a positive match. The scientists have recovered Miko, the Middle Eocene climatic optimum.
Yeah, I think we lost the core catchers that might have recorded the Miko in the last sites. So yeah, it seems to be present here. It's quite cool. Yeah, the deepest site.
The scientists gather as the last core of the expedition is pulled up on deck. The drill crew pack up their equipment and the Geordie's Resolution makes its way back to land. The scientists have completed their work at sea. Mixed emotions come over the scientists as the expedition nears completion.
I would happily go on another cruise on the GR. I love the time on the ship. It's really valuable research that is publicly available to everybody, so it's a big contribution, and it's an honor to come on the cruise and participate. I've used many of a data set from IODP cruises, so I'm happy to come and work 12 hours and contribute something for everybody else.
a huge learning opportunity for me because especially one of the reasons is like I'm getting to see a vast range of rocks in this expedition, which is broadening my entire knowledge, the domain, since I'm I'm in the learning phase, and it's amazing for that.
We've had just amazing results, really. We were a little bit right in some of the hypotheses and wrong in the others, but all of it is very interesting and brings us really new information that will help to progress in the understanding of this whole region, for sure.
After 58 days at sea, the scientists taken their first sights of land. With the ups and downs of the expedition and excitement of recovering core samples behind them, Expedition 371 has concluded.
These expeditions are really sort of well, if you include all the planning and everything, they're just multi-year exercises. But effectively, once you get the science team together and you have a little bit of pre-planning, the entire expedition is nominally 3 years long. It's sort of interesting because the true expedition is only 2 months long. Then people scatter like the winds around the world, go back to their home countries.
While the scientists' work at sea is complete, their work on land is just beginning.
After the expedition, people go back to their labs, but by the end of the expedition, we will have established collaborative research groups. So we walk off the ship with a catalog of research plans and groups of people who work on each topic. And these people will stay in contact for years after the cruise, and that is absolutely critical.
I've been on the JOIDES Resolution 3 times now, and every time has been an amazing, magical adventure. And what's so amazing about this whole program, the International Ocean Discovery Program, is that it's made up of over 20 countries, and where 30 scientists are chosen, the best scientists in the world are chosen to be part of each of these expeditions. And what's amazing is that all the scientists, we work together.
So there will be some really great papers that come out of this expedition. It ended up working out that everyone has plenty of material to work on, and all the scientists kind of collaborate together to work on projects. So it's not any one person has one specific project, but we're all kind of together and we take turns taking the lead on different projects. And that's really great. That's how science should be. It should be collaborative and a group effort. That's when we do the best science, it's when we're together.
The cores are placed in storage and the labs are cleaned. The JOIDES Resolution is in constant motion and a new group of scientists will be boarding soon. As for the cores recovered from Zealandia, they will head to IODP headquarters in Texas.
We are in the Gulf Coast Repository in College Station, Texas. It's one of 3 IODP repositories in the world, the other being in Kochi, Japan, and Bremen, Germany. We have all the core collection starting with DSDP Leg 1, and we have all of the Pacific Ocean Basin, the Antarctic, Gulf of Mexico, and the Caribbean. We have about 150 kilometers of core material. We're currently doing the sample party for Expedition 371, so over the last 5 days we took about 10,000 samples for our science party. Once we're finished, then they will be forwarded to Kochi, Japan, because the area of the world that these particular cores came from are located in Kochi. On the ship, we take a limited number of samples because we do basic analysis on the samples, but the scientists, depending on what they're doing, require different volumes and different resolutions. So high resolution paleoceanography can be up to a single individual can have thousands of samples.
After the sampling party is complete, the scientists will spend the next 2 years working from their home labs before finally meeting again in New Zealand to give their results. While the scientists continue to work on the cores recovered at sea, The true story of Zealandia is waiting to be uncovered.
So it's been known for a while from data from New Zealand and New Caledonia that the world was a much hotter place back when the Pacific Ring of Fire formed. It was a greenhouse world. The climate was much, much warmer. A lot of effort has been going in globally to understand that world. What is it that makes a greenhouse climate system work the way that it works? And in order to do that, you need to collect data from all around the world, and Zealandia is part of the world, and Zealandia appears to have really quite an anomalously hot temperatures during that time period. Why you might find that interesting? Firstly, it may be because there was something different to do with the geography of Zealandia that made it a warm place, or it may be that the geography of Zealandia is poorly known, so we're unable to model it very effectively. Or it may be that we just have poor quality data because it's so remote, and so our expedition can potentially address all of those issues.
Ultimately, it's science. It's really, that's the key thing that stands the test of time. Some people, they become, great scientists. Some people, after a few cruises, maybe, they do something else with their life. But it's the science that's done out here that's always, kept for forever.